Hello, today I'm turning my Vulkan engine from a scrappy one-color renderer into a PBR renderer, and I'll try to explain how a basic PBR rendering pipeline works. Right now, my engine supports meshes and has a hard-coded light in the shader located at the world origin. Geometry facing it gets lit. Today's star model is the damaged helmet asset from the Vulkan API demo assets. As a baseline, let's inspect how it looks in proper rendering engine where people actually get paid. Very nice! Looks like Blender is using an environment map showing a forest, which the helmet is reflecting. This type of rendering is called PBR, or physically based rendering. PBR is a rendering technique based on physically meaningful material properties. The standard pipeline for PBR includes material textures such as albedo map, a normal map, a metallic roughness map, an occlusion map, and an emission map. These maps are interpreted in the shader with lighting data to achieve, well, a physically based result. Back to my engine. I have no problems loading the model itself and displaying it as a gray blob. Or a checkerboard blob. Fantastic! All we need to do now is make all the textures from the GLTF file available to our shader. I first load them from the GLTF model into CPU visible memory. I do this with the help of a library called FastGLTF. I've created a debugger window to verify that the images are, in fact, loading correctly. Now, we need to make those textures available to the shader. In Vulkan, that's done through descriptor sets. Once they're bound, the fragment shader can sample the textures, and we're finally ready to build the material. These textures by themselves don't look all that great. In fact, they look flat. The most important part of PBR isn't having these textures, it's having a shader that can interpret them, together with the scene data like light direction, camera position, and the material properties themselves. Writing a good PBR shader from scratch is way above my pay grade. Luckily, Sascha has an excellent Vulkan PBR demo available under the MIT license. Thanks, Sascha. We'll borrow the ideas and adapt them to my engine. Let's start combining everything. For lighting, I will use a sunlight component, basically a light at an infinite distance that has direction, color, and a strength parameter. Our lighting also provides an ambient term, a minimum amount of light so that shadows aren't completely black. After that, surfaces facing the sunlight are lit more strongly. This lighting is applied on top of the albedo texture. Light is just a bunch of numbers. It's how we interpret them that matters. Honestly, this is already very good, but we're still missing the fun part. Next are the roughness and metallic textures. Roughness controls how scattered reflections are, while metallic determines how much of the surface behaves like a metal and reflects the surroundings. This is what gives the metallic objects their shiny appearance. We already have pretty impressive looking lighting, at least by my standards. Now comes the part I definitely don't understand. Besides acting as the background, a skybox can also become lighting data. From it, we generate an irradiance map for soft ambient lighting and a pre-filter map for reflections. The result is that metallic surfaces start reflecting the world around them instead of looking like plastic. And the result already looks much closer to what we saw in Blender. You can clearly see the reflections of space on the helmet. Adding the normal map brings all the tiny surface details like seams and scratches without any extra geometry. It's a subtle effect, but it makes the model feel much more believable. There are just a couple of finishing touches left. One of them is tone mapping. It converts the renderer's raw output into something that actually looks good on your monitor. I'm using ACES film because that's what ChatGPT told me to use. And now, for the final modification, we have BRDFLUT, or bidirectional reflectance distribution function lookup table. And yes, I absolutely know what it means and how it works. The short version is that it works together with the pre-filter map to make reflections behave more realistically. For example, reflections become stronger near the edges of the object. I can't say I fully understand the irradiance map, pre-filter map, and the BRDF LUT yet, but I do know one thing: they make a huge difference. So this is what we're working with. And yes, I only realized towards the end of making this video that I had the helmet rotated the wrong way the entire time. This is actually the front of it. After all that, I will finally shut up for a few seconds and let you admire it. Looking pretty damn nice. Anyway, there is still a ton left to implement in the rendering pipeline. Shadows, anti-aliasing, bloom, global illumination, post-processing effects, outlines, lines, the list goes on. But for now, I think I've stared at helmets long enough. It's finally time to start making a game. I don't know if I'll end up using this exact rendering pipeline, a modified version of it, or something completely stylized. What I do know, however, is that the renderer is in a much better place than when we started, and I think I'll continue improving the rendering engine alongside the game itself to keep at least some of my sanity. Huge thanks for watching. I hope you enjoyed the video and maybe even learned something new. See you next time when I finally start making the game. Oh, and please subscribe.